All right, I'll just start now. Welcome everybody to this episode of the Multiphysics channel. Can I ask people, can I ask to mute the microphone for the moment? And then afterwards, we will have a Q&A session where you can ask your questions. So welcome to this episode of the Multiphysics channel. This is the last episode of this season. For a reminder for the ones that joined us just recently, so this is our initiative to build a knowledge base and to bring modelers together. We start this initiative at Empa, but we are soon expanding over to Switzerland, and then eventually we will take over the whole world. As a Christmas gift to you, I'm going to show you here how Santa flies at a very elevated speed, and then on side of that, I will also show you some tricks with COMSOL, how you can convert sketches or JPEGs to geometry files, or how to solve delicate problems. But first, something about me. So I'm Donato Rubinetti. I'm your host today. Since the last time, the first episode I gave 2 months ago, not much has changed. I'm still a mechanical engineer, and I'm doing all about modeling. I'm in my first year PhD at Empa and KU Leuven, my home university in Belgium. A curiosity about me, and I just discovered recently, because now it's orange season, that I really don't like sliced oranges. I can't peel and then eat them. I just have to squeeze them. And in that picture there that you see, that is me at the top of my happiness, drinking a cup of freshly pressed orange juice. I'm going to show something about Santa today, but it is not my first experience with Santa. Actually, I have been doing some stuff already. In 2006, for example, I was delivering gingerbread to pupils in our school. Then 8 years later, I actually dressed up as a Santa and I acted for my 5-year-old niece. In 2020, that is today, it is my first CFD simulation of Rudolph and Santa, and I will show you how we got there. So a bit of background story. This is a holiday Christmas card that has been sent from the German Aerospace Centers 10 years back. And that inspired our friends from Windisch to perform an experiment in their sonic wind chamber. And me, I'm doing the simulation here about that exact experiment. I'm from the Symbiosis team at 401. And in this episode, you will learn how to convert images to geometry and how to ramp up convergence for delicate solutions. So let's get started right away. So we have a picture like I showed you before in the experiments, like this one, which is a quite complicated geometry. And you want to make a simulation out of that. So what you need to do is you want a model. And you want a model geometry like this one. By the way, if you have questions, you can ask them in the chat and I will answer them afterwards, or you can just say it afterwards yourself. So one way to convert geometry like this into a model could be that you do a quick and dirty tracking of the points, and then you would have to click along the line, and then at the end you would get some text file with X and Y coordinates. But there is an easier way to do so. If you go to COMSOL, in that tab Developer, there is an add-in you can load in, and that has the functionality image to curve. And when you load it image to curve, then you will be able to convert pictures, JPEGs, even your hand sketches, whatever it is, you can convert them into a geometry file. I will show you in a second how that works in practice. Now, the simulation I showed you before, the picture is Supersonic CFD calculation, and that is a quite delicate one. Why so? Because you have elevated Mach numbers. So I remind you, the Mach number is the ratio between flow velocity and speed of sound. And when you transit from a low Mach number flow that is below Mach 1 and you go up to higher Mach numbers, so you will cross different stages of the flow field. And if you jump right in with 1.5 Mach 1.5, the chances are high that you will not get a solution. And why is that? Because this is very difficult simulation. All right, for that reason, I use the auxiliary sweep. The auxiliary sweep works similar as a parametric sweep, but it is sort of helpful to ramp up the solution. So you have, let's say, for example, even if you have some sort of force that is constraining your flow field, you can stepwisely increase the solution and then get to the value that you actually want. But you start from a lower point first. So you approach the solution step by step. Good. The two things I talked about, I'm going to show you here in this model that I prepared already. So here in that tab, developer, you would find the add-ins. When you go to add-ins, and then you have here add-in library, you can choose one. And then you have here in this library, you have the image to curve add-in. You can just click on that, and then it will be loaded in. I have it loaded here already. It is found under global definitions. Let me show you better. Here, image to curve. And that is a really nice trick because you choose just simply your file. It is a picture file, and then you plot it here. And then what you see in the graphic window is basically the image itself. By the way, from the experiment I showed you before, I did some editing here. I used a gray brush to erase that stick that was at the end. And then when you go to contour here, you can, the software itself will find out where is a contour that is worth drawing. So you have to adjust the threshold. The threshold is found here. I put the threshold 0.14. If I increase the threshold, it will take different areas of the shaded file. So that is definitely not what we are going to want for the geometry afterwards. Once you have done this, and then now we go back to 0.14 as it was before. Once you have done this, it will automatically load that curve here into the geometry node that you find here. Yeah, it adds by default this interpolation curve with this image IC and here this scale IC, because you also have to give some sort of reference. How long is that feature in the end? Good. Once you have imported the curve, and that is, as I said, automatically, I chose here to have this converted as a solid. That means afterwards I can easily perform an operation like taking away this shape from another solid domain, and it remains just blank. And that's the walls we afterwards want. All right. This is how you convert an image to geometry. I think it's very convenient. Even if you do some hand sketches or something, you can then just import it without having to construct it with the tools here in geometry. All right. When I run this calculation, of course, I won't get a solution because it is a way too fast calculation. So in this entrance here, we have Mach number flowing in. So it is about 1,000 kilometers an hour of an inlet. So that's quite massive. And here we have an outlet. And in between here, in that region, a certain flow will develop. To get convergence, I'll ramp up the solution. I take it very easy at the beginning. And here you see that I chose the parameter Mach number as a ramp up parameter. So I start from 0.5, then I take steps of 0.2 up to the region where is Mach 1. So that is the most delicate region. So I will ramp up just 0.05 afterwards to see what happens there. And then I go all the way up to 1.5. By the way, what do you think? How long does this calculation take on a workstation? Make a guess and write it in the chat if you have an idea. Good. And now for the flow field that I want to show you as well. Here we are already in the high Mach number, but let's just start from the very bottom. So the whole geometry here is, the center is about 3 centimeters. So it's a small model, right? Just what you would use in experiments typically. You have this inlet that comes in with this certain velocity and pressure as well as temperature. And here you can already see that on very small space, the temperature varies quite a bit. So it goes from 2.7 degrees Celsius up to 11. I hope it's big enough for you to see. And now I just continue ramping up the velocity. And the fun thing is that here I'm plotting the Mach number on that area. So even though at the inlet we are still under Mach 1, we have locally, because of some expansion and compression effects, we have, especially here at the nose and at the heel of Rudolf, we have Mach numbers that are all the way up to 2. And that also shows why it's actually so difficult to get convergence here, because locally you want to calculate with a set of equations that normally you wouldn't do. Then I continue. So we are crossing now the sonic barrier pretty much. And as more as we go, yeah, now it happens. So we have some sort of detachment, and behind it, there is high speed flows as well. Before, it was more like, yeah, it's taking this sort of wake, and there is dead water. So its velocity is equal to 0. But then it goes further up and starts increasing even more. And that's how the solution looks at the end. So here, look, what I want to point out is that on very short space, you have quite a huge drop in properties. So for example, pressure goes from 1.2 bar to half bar. Good. That is actually already it. There is much, much more that you can analyze with this model. You could do a mesh analysis. You could try to find out what is exactly happening where, but I guess that I'm sure even the most expert people among you will take hours to understand fully what is happening with the flow here. All right, let's go back. So this was it, the ramp up of convergence and the convert images to geometry. I showed you how to do so. The highlights of this episode, we are already coming towards the end. I showed you how to convert pictures to geometry, and I showed you that because for me it was really it really stepped up my modeling game by doing so. I also showed you how to ramp up convergence with an auxiliary sweep, and in the end, of course, happy holidays from our team, from all of us, and enjoy the time despite being so difficult. 2 more things I want to mention. So we have this machine learning event at Empa that will be on the 20th of January. And just 1 day later, we will be back with the 2nd season of Multiphysics channel. There it will be for real modeling real world problems, so real applications. Make sure to join. And even if you have some experiences in modeling, so whatever it is, we are always looking for motivated people, and we have still some free spots for the 3rd season, which starts in April 2021.